Okay, this is like my future. Okay, I mean, like I'm doing the same derivation of as in the previous two launches, but I'm doing this in terms of using David Tongs Lectures. So we got I'm working on my Windows side. So now what I have is that the Lagrangian is equal to the integral of the Lagrangian density with respect to the field and the partial of the field, the volume. Right? So we build it. Lagrangian is equal to the integral of the Lagrangian density as a function of the field and the partial of the field with the whole volume. Lagrangian is used to capture the equation of motion, and we say that the dynamics of the field is governed by the Lagrangian, which is a function of space. From the Lagrangian we build the action. So where the action is equal to the integral of the Lagrangian with respect to time. So with respect to integrate the Lagrangian with respect to time, and then using the definition of the Lagrangian, we get that we integrate it with respect to time and integrate it with respect to the volume. We integrate Lagrangian density with respect to time and the volume. We get the four-dimensional integration of the Lagrangian density. And when we build this, we get that the action equals integral of the Lagrangian with respect to time, and we got the four-dimensional integration of the Lagrangian density. So now, there's a definition of Lagrangian density. In particle mechanics, the Lagrangian density is a function of Q, which is the position, and P dot is the momentum, but not a function of QW dot. In the field theory, the Lagrangian density is a function of the field and the dot of the field and the partial derivative, spatial derivative of the field. And does not depend on phi double dot, the field double dot twice, and the second derivative or second order derivative to the field. We determine the equations of motion by principle of least action. So we build it. Okay, that's what we have. Lagrangian density, particle mechanics. Lagrangian density is a function of the position and the momentum, but not as a function of the sort of like acceleration. In field theory, the Lagrangian density is a function of the field, the dot of the field, and the spatial derivative of the field, and does not depend on the phi double dot and nabla squared of the field integral equation by principle of least action. So basically, what we have now is that we have to vary the action, as my colleague would say, extremize the action. And there it is. So this gives us a change. How the field changes from the initial state to the final state. Right. So that's the equation we're looking for. This will give us the variation of the four-dimensional integration of the variation of the Lagrangian density. That will build it this is where it becomes variation integral for dimensional the Lagrangian density. Now we have that. This gives us the integration for dimensional integration of the partial Lagrangian with respect to the field, and then the variant with field plus the partial the Lagrangian density with respect to the partial of the field, and then vary the partial of the field. And if we build this, it becomes there. So that's what it is. We bring this up. So it is equal to the 4-dimensional integration of the partial of the field with respect the partial of the Lagrangian density with respect to the field, varying the field, plus the partial of the Lagrangian with respect to the partial of the field, varying the partial of the field. So basically what I've done here is that I've just separated the two terms. So there's the initial term, first term and second term. So I just made it the first term integration, 4-dimensional integration, the second term, so that I can perform the integration by parts on this term. This we get to the next line, then to show this. Now first I swap around the variation. So now I just put this into the curly brackets. Again. Now what I've done is I've swapped the variation and the partial, because this does not act on the partial, it acts on the field. And then from here on, then I can perform the integration by parts. Going to give us now 3 terms. So basically, this is what we have now. The first term, second term of this term over here. The endpoints, this is going to vanish, and then we're left with this term and that term. This, so I can see it. There it goes. Now I've got the 2 terms in the curly bracket. So now I have to take out the variation of the field. So if I take out the variation of the field, I've got this is like the whole action. Now for the action to disappear, this term must disappear, which is then given by was okay. Then so I just rewrote this as the integration of the 4-dimensional. Then, okay, the boundary terms vanish for any variation. So the variation of the field that decays substantially fast at a spatial infinity and obeys the fact that the variation of the field at the initial time is equal to the variation of the field at a later time, t final, which is equal to 0. So now we must then have that the partial of the Lagrangian with respect to the field minus the partial of the partial of the Lagrangian with respect to the field is equal to 0. There it is. There are the Euler Lagrangian equations of motion for given Lagrangian, which is a set of fields. The example is the plane Gaussian equation. The Lagrangian is equal to, okay, this is like an example that we're doing. So it will give you the Lagrangian is equal to have the Minkowski matrix multiplied the partial of the field, partial sub mu of the field, partial sub mu of the field, minus half m squared, phi squared. So we can expand the Minkowski matrix this can be achieved. So where the Minkowski matrix, okay, the eta superscript mu is the Minkowski matrix. So using it and expanding the equation, we arrive at this equation. Where is that equation? It refuses to build. Okay, did build. There. So, okay. Okay, and then put all these terms together, make it all neat. We do this thus. This is what we get the Lagrangian is equal to half phi dot squared minus half of number phi squared minus half m squared. So this like represents sort of like the kinetic term, and this is going to represent a potential. These two terms represent the potential of the system. So I rewrote this, so I'm writing it as classically it would look like you got a potential function of velocity. So, but this is not velocity, it's like phi dot of the field, and this is like the potential, which is like representing those two terms. And then if I build this, the rewriting the Lagrangian is equal to the new definition that I wrote there. Should have called it like some fancy name.